In this video, we're going to talk about the difference between distance and displacement. The term delta x is what we're going to use for displacement. Little triangle means change. And so if x is position, then the delta x is the change in position. This can also be expressed as the final minus the initial. And there's a lot of different ways that these subscripts come out. Sometimes you might not even see a subscript here for final position, and you might see x naught. So x naught would be the initial, and then x with nothing is the final. And there's different ways to do it. You might also see x2 minus x1, or whatever interval that you're specifically looking for. And I traveled from house to school, right? This could be considered position 1, and this would be considered position 2. Now, a distance that we usually talk about, how far from the school is your house, the distance that you would travel would be expressed from here to here. It's a straight line. Now, in this case, the distance is equal to the change in position. They're equal. It's not always the case. I could have my house, the school, I might start at the house, but then travel around, I hit a couple errands, I pick up my friend, we go to the park, we hang out, and then eventually we get to the school. Now, this D is the path I traveled, that's the distance. And I put a lot of miles on my little pedal bike getting to school if I took this very circuitous route. And that's different than the displacement, because I'm still at position 1 here, and I'm still at position 2 here. This displacement didn't change because it's based on the straight line distance between those two objects. There are a couple other ways to think about this. Because this is position 1 and that's position 2, displacement helps us understand if I'm going from my house to school or from school to the house. And we'll talk about vectors in a little bit. But if I'm going from the house to the school, then this becomes my initial position and this becomes my final position. But on the other hand, if I was going from school to my house, well, then this would become my initial position and this would become my final position. And you make it even more complicated. What happens if my initial position is the same as my final position? So I go from my house in the morning, take the bus to school, I sit in school all day, and then I come back home. Now, from that time to that time, from when I left the house to when I got back to the house, I haven't actually really gone anywhere. My displacement would be 0. You can look at it the same way on a racetrack. If you have a start line and a finish line, when those cars go around the racetrack and they do their 200 laps, they've put in a lot of miles on those tires. They probably changed a few of them, but because I started, my marker's down. Because I started here and I got my checkered flag here, they're the same position. So my displacement on a race is actually 0, whereas the distance that my wheels traveled could be upwards of 200 miles. Okay, so if we're talking about an average velocity versus an average speed, we would express that v AVG is equal to displacement over the time interval. And then average speed would be equal to the distance over time. If the velocity is changing, so for example, if you were going from home to school and you started out, you were going really, really slow, maybe you were going 8 meters per second. And then you come across the large barking dog and it scares you and you speed up and you go 15 meters per second. But then now you've gone so fast, now you're tired, and so you're going to school and you're only moving like 2 meters per second until you get there. You were moving at varied velocities over a given time, okay? And so what we can do is we can take kind of the average of these. If I just look at how long it took me to go this distance, all of these individual or instantaneous velocities would be adjusted. There would be evened out, once you get that average. Distance doesn't really take into consideration any kind of direction. And so average speed for like a race car driver, right, could be 200 miles an hour. If he's starting here and he's driving around this race car track, he's going to go 200 miles in a given amount of time. And so in that 200 miles, maybe it took him 3 hours, right? If you ever watch NASCAR on TV, you know, watch cars go around in a circle for 3 hours, you know, you're looking at speed because their velocities are changing. They're pointing their car in different directions all the time. Okay, so it doesn't make sense to calculate all these velocities. We just focus on speed going around the racetrack. If the velocity does not change, it's called a constant velocity. It's moving at the same speed and the same direction. So if I was going to school and I was just walking the whole way, and I went from 3 meters per second very consistently the whole way. So constant velocity meaning it wouldn't change and the direction doesn't change. If I had to make a detour and go this way, then this way, then this way, and then this way again, okay, I changed directions. That's not constant velocity anymore. Okay, let's do a couple examples. Swimmer A goes across the pool, a 50-meter pool, in 25 seconds. Swimmer B goes across that same 50-meter pool in 100 seconds. What is their average speed? I can only say speed because I don't know which direction they're swimming. Okay, and so 50 meters in 25 seconds give you 2 meters per second for swimmer A. Swimmer B is going to do 50 meters in 100 seconds, and so that will be 0.5 meters per second, much slower pace. All we can say is their speed because there's no direction involved. Okay, so swimmer A started on this side of the pool and went down here and she finished over here. Swimmer B started over here and finished over here. We already know that swimmer A is swimming at 2 meters per second, but now because she's going to the right, I can say that she's swimming positive 2 meters per second. So the displacement here, if you say your position position 0 or initial position, and then right here is her final position, and she's going from the initial to the final in that direction. Swimmer B starts over here at the 50 and comes back to 0, and so this initial position and this final position produces a negative value. So when you do the velocity delta x over delta t, what we're really looking at is x minus x naught over the change in time. And so when you plug in 50 and 0, you end up with 0 minus 50 in 100 seconds. And so that produces a negative 0.5 meters per second. And so these positives and negatives help us understand which direction the swimmer is going, and it's more informative.